said up here that a line is determined by two things. Now in two-space, you're very familiar with that. You know that if you have a point and the slope of a line, that completely determines the line. You can get the equation for the line, you can graph it, you're all set. Well, I want to generalize that to n space. Now n can be 2, so we're going to come up with something that still works in 2 space, but that will also work in 3 space. And the notion of slope doesn't work in 3 space, because basically what this does is this indicates a location where the line will be, a point that it passes through, and the direction in which it heads. But if I'm in 3 space, I can't indicate a direction with a single number, because slope is a fraction. It's rise over run. So it has 2 parts to it, the rise and the run, giving me the vertical and the horizontal change. But if I want to indicate a direction in 3 space, it takes 3 numbers to do that, because I need to indicate how far out we're going, how far left or right, and how far up or down. And so that's 3 numbers, and I can't fit 3 numbers into the 2 parts of a fraction. So what we need to do is indicate the direction another way. So in n space, and again, n could be 2, but it could also be 3, I'm going to need a point. Again, that's going to tell me where to put the line, and I'm going to need to indicate a direction with what I call a direction vector. Okay. So we're going to replace a numeric slope, which gives us the direction of a line in 2 space, with the notion of a vector that gives us the direction of our line. Let's just take a look at an example. I'm going to do an example in 2 space so that I can graph it completely accurately. Well, close enough. Okay. Let's suppose that I want a line that's going to go through the point 2, 1, and I want the direction of the line to be determined by this vector v, and let's say v is -1, 1. Now certainly that gives me enough information to graph the line, because all I'm going to do is just extend that direction vector v infinitely far in both its direction and the opposite direction. That's the line that goes through this point in this direction. Okay, so how do I come up with an equation for that? Well, I'm going to say r of t is equal to, okay, and I'm going to refer to this point as my starting point. Lines don't really have a starting point, but if I write it as a vector, I can write it as r naught. That's just going to be the r value at 0. So I'm sort of thinking of 0 as my starting time. Obviously, there are negative times before 0, so we're not really starting at any particular time. But I'm going to sort of informally call this my starting point. So I'm going to start with that. So I'm going to take this point, I'm going to write it as a vector. So r naught would be the position vector that points from the origin to that point. So I'm going to have 2, 1. That's my starting point. Okay, that puts me on the line. Now, I've graphed it here as a vector, but remember, when we're actually graphing a vector function, we're just going to graph the tip of that vector when it's in standard position. So when I'm graphing this, and I'm not done writing the equation, obviously, or I just have a single point. When I'm graphing this, this is going to give me that point. Okay. Now, if I want to get to another point on the line, what I'm going to do is I'm going to go in the direction of v, or in the opposite direction of v, a certain distance, to get to another point on the line. So I can add to that a multiple of v, which we said was -1, 1. Okay. So essentially we're saying r of t is just my starting point plus t times my direction vector. That gives me the vector equation for a line. Now, I introduced this notation of vector functions in the last video. I may have inadvertently lied and said the book doesn't introduce this at all until chapter 13. Chapter 13 is actually completely devoted to vector functions, but the book does introduce this notation just for lines in this section. So this would give me the vector equation for this line. Let's explore that just a little bit. Now again, remember when I'm graphing this, I'm going to be graphing infinitely many points, not infinitely many vectors. But in understanding the way the equation works, it can be useful to graph just a few of the points as actual vectors. So let's just take a look at what I would get at r of 1. R of 1 would be 2, 1 plus negative 1, 1. Okay, so that's my starting point plus 1 copy of my direction vector. So that's going to be 1, 2. Okay, well, let's see how we get there. Here's 2, 1. Here's 1 copy of v. Now, right now, I've drawn it so that the tail of v is at the tip of r, which is how I do r naught, which is how I do vector addition. So this vector right here would be r of 1. And you'll notice it does look like it's 1, 2. Now, of course, when I'm graphing the line, I'm just going to graph the line. I'm just graphing the tips of these vectors. But by graphing it as a vector, I can see how this formula takes me to points on the line. Now, if I wanted to get to a point on this part of the line, my t value would simply have to be negative, because I'd take r naught, which would take me to a point on the line, and then I'd add a negative multiple of t that would take me to some point on this part of the line. Okay. So that's how the vector equation for a line will work. Now that gives me a single equation for that line. Of course, if I wanted to write the parametric equations, I could. Notice, if I actually did the vector addition here, I could combine these two vectors and say r of t is 2 minus t, 1 plus t. I basically just scaled each component here by t and then did the vector addition. So my parametric equations would be x equals 2 minus t and y equals 1 plus t. The parametric equations just become the component functions that I have for my vector equation. And it's not actually necessary even to write it like this. I could pick that out from here. I could just say x is my starting x value plus t times the x component of my direction vector. And y is my starting y value plus t times the y component of my direction vector. Excellent. So let's try an example in 3 space. I want you to find me a vector equation for the line that passes through the point P, 1, 2, 0, and Q, 3, negative 4, 2. I just want an equation for the line through these 2 points. I'm not at this point specifying an orientation. So I don't care whether it goes from P to Q or from Q to P. Sometimes we will care about the orientation. Sometimes we won't. This is one time where I won't. That means there's going to be more than one correct answer. There would be, even if I did specify an orientation. You're familiar with the fact that in 2 space there's more than one equation that correctly describes a line. But go ahead, pause the video right now, see if you can come up with a vector equation for this line. Welcome back. Okay, so I need 2 things. I need a starting point. I've got 2 very good options, P and Q. I'm just going to choose P, but I'm going to write it as a vector. So I'm going to write it as the position vector that points to that location. Okay, and then I need a direction vector. And again, I've got 2 very nice options, either PQ or QP. I'm going to go with PQ. Okay. And if I'm doing that, I'm going to calculate the components by subtracting. Just remember to subtract the components of Q minus the components of P. So it'll be 3 minus 1 is 2. Negative 4 minus 2 is negative 6. 2 minus 0 is 2. So I could say R of t is equal to 1, 2, 0 plus t copies of 2, negative 6, 2. That is a possible answer. Other possible answers you could get, you could have used Q as your starting point, and any non-zero multiple of this is correct for your direction vector. If I had specified that I wanted to have this orientation, I would have to use any positive multiple of this. A negative multiple of this would reverse the orientation, but any multiple of this would do. So if I wanted to, I could say, let's just multiply that by a half. I could have used as my direction vector instead 1, negative 3, 1. That points in the same direction, but I'm just using smaller numbers. Okay. So there are always going to be lots and lots of options. Now, do be careful. I specifically asked for a vector equation for this line. So if I ask for a vector equation, I'm looking for something like this. I don't care whether you leave it as a sum of two vectors or you combine into one vector, but I am looking for a vector function, a single function. If I asked for parametric equations, plural, equations, then I would be looking for what's x, what's y, and what's z. So the corresponding parametric equations here would be x is 1 plus 2t, y is 2 minus 6t, and z is 0 plus 2t. Okay. Do make sure that you read the directions. If you are just asked to parametrize a line, either one works. This is parametrizing the line, this is parametrizing the line. Parametrizing a line simply means that you're describing the points on the lines in terms of a single parameter, which would be the parameter t in this particular case. All right?